Hello everybody, this is Schwab again. Uh, at this presentation I'd like to continue the explanation about post-processing of general equation solvers. This time we'll focus on 3D FEM, and as we've seen in 2D FEM we were using streamlines for tracing particles. We can do similar stuff also in the 3D FEM. I'll open here a very simple project. This project is showing a flow domain which is kind of quite simple. If I show you the full shape, that's the full flow domain. We have a rectangular entrance. The polymer flows in and then is squeezed to a smaller area, and so that when we look at and use the symmetry and look on only the 1/4 of the geometry, we see that the polymer gets accelerated and stretched. Well, it's not that important for really this explanation, but we just need a simple geometry to play with. So of course I can do cuts and isosurfaces and other stuff, but because the polymer flows, it would be very nice to see how it really flows, to see some path lines, some particles flowing through that geometry. Now we can do it in many different ways. First of all, I can go to grids and click here, create a path line, or here in operations too. Basically, whenever I click, a temporary grid is created. This grid is dependent. It depends on the parent grid from which it takes all the variables and calculates just on demand the variables. And also, this particle tracing is based on the velocity field, which is solved on the parent grid. So that velocity field is traced forward and also backward from a certain seed. Now the seed is this small yellow point there, and I can just move my or change my coordinates to be seeing that this yellow point is moving here. And if I decide to use that point, I just can click set, and now my seed has been set, and from that position downstream and upstream the path line was calculated. Now, of course, I don't see the path line because the front faces of the parent grid obstruct the path line, so it's not visible, but it goes through really, and we see a graph. So maybe we can just hide the parent grid, and now we see the path line coming through. We don't need to hide the parent grid. We can just hide the front faces. That is this icon here, which is used for. So now we have hidden the front faces and we see the path line coming through. Also, I need to explain that when we are looking at the path line, we always have lots of different variables to look at. For example, on this path line, I can basically look at all the standard variables which we see also here for other types of grids. But we have, let's say, like pressure, temperature, and so on. But we have some extra because Pathline has also a time, so we can look at the time as a function of the length. We can use also other variables, for example, strain. Strain, it tells us how much do we stretch that particle, and we know that, well, look, this particle is stretched maybe 0.65. That's not too much, but if it exceeds number 3, if we stretch it 3 times, then the particle or the polymer is known to start to sort of break. Well, of course, the polymer molecule won't break. What breaks is the continuity, and in a certain way, you can imagine that the polymer is a network of springs, and these springs are being stretched too much, and they don't handle simply that fast stretching. So usually when the strain is large and when it happens in a very short time, we get instabilities. Now, one thing you have to understand is that when you define a seed, let's say in the middle of that flow domain, whatever is before that seed has a length and time negative, and what is after it has a time and length positive. So if we go just before, see the length here is minus 7.9. So if we just go right where we have the seed, this is the time close to 0 and length close to 0. And as we go forward, we start to have length and also time positive. Okay, the same would be if I just switch to time. You see this is 3 seconds from that seed. Okay, and at the end we have 7 seconds left from that seed. So the total time the particle stays in the flow channel is 7 plus 3, which would be about 10 seconds. Now we have here a possibility to look at all variables as a function of length and time. Why would we do? Why would we need to look at the variables as a function of time? For example, so that we can integrate, because many people know that the polymer can stay at a certain temperature for a certain time. So if you know the temperature, because the temperature is of course part of the calculation, you can integrate that temperature, but you need to integrate it as a function of time. And then you may see the value here. And I don't know, somebody knows, let's say that if the value exceeds 8,000, you can get polymer burning, right? Because the integral of the temperature over time, that what matters, and that what makes the path lines to burn. So these options are also possible. Now the path line in this case is of course 1 pixel size, it's gray, so it's difficult to see. I like the path lines to be like this, but some people may prefer to have a different color, more thick. So the only thing you need to do is just to change the display option set used. So you can just go here and say, let's say that the color of those curves will be, first of all, we can make them slightly thicker, or we can make them different color. For example, I use some green color, or you know what, let's use white color for now. And you see, that's my path line. Now it became more visible, and we see the point moving on that path line. Of course, I can define any other path line very simply. First of all, I can just edit that one if I repeat that operation, or because the program still remembers the last operation was definition of path line, so I can just right click and I can now move that point anywhere to a different position. Of course, I can use picking of the coordinates. So if I hold Control, I can pick the element, and from that element I can pick I can take the coordinates. So let's say from the middle of this square I get a new sheet, and then from there the path line is calculated. Of course, we can do also any other path line, and that's very simple. We just put focus to the parent grid, and now we start the operation again, or we right click again. So now the program understands that, aha, he's on the parent grid, so probably he wants to make another path line, not edit the previous, but make a new one to go to a different position and just click set. And we have now 2 path lines coming through. Now, of course, these 2 path lines are difficult to distinguish because we don't know which one is what. Is this one the upper one or the bottom one, right? So we can just rename them, let's say path 1, and make them, let's say, being called red, and that path line can be renamed hitting function to path 2, let's say blue. And now, of course, if I want to see them in different color, I can edit that display option set now. However, they are both using the same display option set. So if I change the color of this one to blue, the other one will be blue too. But we have something different here. We have here a possibility that the color of the curves is using a grid color. So it is white unless you specify a grid color. So let's specify a grid color for each one of these. So I can just say the red color will, the color of this grid will be red. And we see which one is red, and that one, the grid color will be blue, let's say dark blue, and we see the blue color. So this way I can make the path lines to be having different appearance and different colors, and that helps me to create easy to understand pictures and easy to understand animations. We also can see that when I'm moving in the graph, I see the cursor. First of all, there are 2 things. I can see the seed always. You see the seed is having the, normally, if I just create another path line, I can do that like this. let's say now I do the path line from the end, so we'll trace backwards. You see, normally the seed is green. However, if I change the grid color of that path line, it's already getting the color of that path. So the seed is telling me also which path line it is. So the seed and also the point, the cursor on the path line, they can be also set up. I can set up here in the dialogues APP, which is application settings. I can set up a appearance of these entities. For example, I can say what is the color of the seed, whether the seed color uses the grid color if there is such, or I can say no, it will be all green. So now whatever path line I'm on, it's always shows me the green seed, right? We also can do the same for the graph colors, and we can also define the size of the seed or size of the graph point, graph cursor. So let's say if I just make it bigger, smaller, it just reacts to what I want. So these settings are quite important because everybody's using slightly different screen resolution. So feel free to experiment here. Also, you can see that if I'm, let's say, on the parent grid, I don't see any seed, any graph point. And that's because I just say show the seed only when you're on, and I can of course check that, and you see now all the seeds are visible suddenly, right? So if I just, even if I'm on the parent grid, I still see the seeds, which is sometimes also quite useful. Similarly, you see that the graph point is not visible, but if I just say always, I will have that graph point whenever I'm on a path line, but I don't have the graph point when the graph disappears. Okay. We can also see that we have the possibility to change the size of the seed in two different ways. We can either set up that it is made in units, and if it's made in units, I can specify what unit. So this, if I say 1 here, it will be 1 millimeter in size. And if I just zoom up or down, it just scales down and up too, because it is always 1 millimeter, which needs to scale up and down. However, if I say I want the size in pixels, and I can define, let's say, 10 pixels. Now this ball will be size 10 pixels no matter of the how do I zoom. So this is quite handy, and we in most of the cases use the pixel size. Similarly, we can proceed with the graph point. However, the graph point has one more option, and that is the markers ratio. We've seen the markers being used for the variable, right? On any grid, I can put markers, for example, like this. If I just use a velocity, I can see these are the markers, right? Some indicators which are linked to a particular variable, let's say velocity magnitude. If I use pressure, it will be scalables. Now, each of these variables is linked to some extra variables used to markers. We of course, when we're looking at any variable, they are all scalars, right? However, some of these scalars are coming from vectors. Let's say velocity magnitude is clearly coming from velocity magnitude vector. So if you just using pixels, it's a ball. But when we say we want to have a markers ratio as a cursor for the graph, now suddenly my cursor is having the shape of the marker. Now that is very useful because I can now see the velocity and I can understand the flow pattern and understand how the polymer flows, right? We also would like to change the appearance of those markers, and that's all being done here in the markers. We can set up the appearance of scalables, vector marks, tensor marks, right? So we also can see that the that here, if I, let's say, try to modify the vector mark, I can change the size to, let's say, 50, and of course the ball is now much bigger, or I can say scale by value, and now the vector will be bigger in the large velocity area and smaller here. Well, that's again relatively dangerous, because if you go to a velocity or to a path line where the velocity is much smaller, we will see that the path line, the marker the arrow becomes sometimes so small that we can hardly see it. It's over there, and it's big only in the larger velocity. So that is sometimes dangerous because you start to you may not even observe that arrow. So don't scale above it. I don't recommend to scale it down unless you really um, really want it. We also can choose, let's say, a conical shape of those arrows, and you have lots of options here. Just try to experiment with those. And also I should say that we have here other variables. Let's say if I just use the temperature, pressure, they are not linked to a vector, so they will be visualized only as scalables, and you can again set up the scalables over there. We also have variables which are linked to a tensor. That would be a stress magnitude. So you can see that when I'm looking at this particle, I can see some kind of shearing. That cylindrical ball is basically showing me what is going on here. There is a shearing. Now we see some elongation, and then again slowing down. So that's expansion. When we look on the other path line, we won't see too much shearing because now we're in the middle of the stream, and then we see more elongation rather than shear. Okay. And of course, if you are having a path line which is very near the wall, then the shear dominates. If you have path line very close to the middle, the elongation effects dominate. So this is really showing a scale which is coming from a tensor. So the marker is being displayed like that. Okay. Now let me delete those path lines. I'll make here a new one, and we can also see the markers on that path line, right? Because even the path line is having some nodes, and in those nodes we can see those path lines. You can see that the graph is slightly bigger than the markers being used for the nodes. That's because here in the application settings there is 1.5 stan. So this is 1.5 times bigger than the regular markers. Of course, if you make it 1, your marker becomes exactly the same as these things. Well, if you make it smaller, let's say 0.7, it can happen that the marker becomes obstructed or hidden inside, so we don't want that. We usually want that slightly bigger than, let's say 1.5 is a good size for that arrow. Okay. And there is one more thing hidden here in the grids. You can say use time marks, and if you do that, your path line is covered by lots of markers. Right, there are balls, but that's because here we use we simply assume we want to see balls. But if you say prefer extra variable when marker is on, they will come to an arrows. Now that is very handy because we can have a picture showing us or get us more feeling of the speed in different segments of the path line. And here we can also use the delta, you see, so that way I can just make them denser or less dense. Okay, so if I just do this, now these markers are placed with the same time increment. So you see there more distance here because the time here and there represent different distance. So that's why we have them in different distance. And of course, if I would define another path line, which would be flowing, let's say, very close to the wall, so flowing relatively slowly, we would see immediately that we have very different number of arrows. Okay? So now we have two path lines relatively close to each other, and we see the difference in distances, and that gives us some other understanding. These arrows are having white color. We of course here in the markers can set up that the vectors have arbitrary color you like. So you can say I want to use, let's say, color of the variable. Similarly, we can decide to use the grid color, and if I have any grid color, they would be different color, let's say red for that one, blue for that one. So you can play with this a lot. So now I will show you a very interesting way of doing the path line, the predefine, and that is I already have prepared on the disk C, I have here XYZ text file. This text file is very simple. It has simply number of seeds, and these are the coordinates of the seed. So this is XYZ of the first seed, XYZ of the second one, and so on. Now, the only thing I need to do is just go to XML command and say create pathlines from XYZ file. And once you do, you see that one by one, these 4 pathlines have been created. Maybe you don't see them, but these seeds are there. Now, of course, the program made them in a folder. You know, making something in a folder is very useful because we can just hide that folder and the 4 pathlines are gone. Or we can just give them at the same time the same variable like pressure, temperature, etc. Right? Now these pathlines these are the seeds. If I just click on them, you will see the seed. This is seed for the second one, and so on. So they were not started at coordinate Z0, but Z5. If you look back at the file, it was really having Z coordinate 555 over there, right? So nothing's easier than just erase those pathlines as the whole folder, and you can just edit that file and say again create pathlines, and it just repeats that. So now you will really value that if you have like 30 of them. This is really very fast and very automatic way. At the same time, you can just post-process any of these pathlines as you normally do. So that is a nice way. Similarly, you can do the same thing with the ZR alpha. There is also a potential that we can export that pathline. There are several different ways how you can very efficiently export data of these pathlines to a file. One way is to click on that particular file and go to appropriate grid, and then in the and go to the dialog, and then in dialog you can set the variables you're interested in, let's say velocity, magnitude, and then let's say you can compare pressure. Now these 2 variables will be exported simply by clicking here and saying save as an ASCII file, and if you just go to the particular folder, you call it trial, and we go there, you will see that my text file is containing the description of the variables and then these points, which are very easy to just copy and paste to clipboard, and then you can compare those files in the clipboard very easily, and make fancy graphs and elaborate it. Here I'd like also to show you a new feature of the version 6.9, and that is the way that we can export every grid to a file. It's been initiated by a simple export import command, export grid data to a file, but we should understand how it is defined. First, in your users folder, find in the appropriate user application data roaming CompuPlus 6.9, you'll find this split header txt. We'll be talking about the split definition later on different part, but if you try to locate in that file the grid values, you will see that this particular segment is used for exporting the pathlines, and here we define simply the secondary variables, and we can put here a list of the name of the variables to be exported with the pathline. There will be, of course, primary variables exported. These ones are secondary. So you can put a list of 10 different variables, or none if you like. If you just comment this out, it will be not exported at all. But let's just keep it there. And if I go to export of that pathline, export to this file, which is having 3 primary variables, 2 secondary variables, which those are the ones which we define, and then we have an identifier for the first node, the 3 coordinates, then this is the primary variables here, and these ones are the secondary variables. So that is the pressure, that is the stress magnitude, and again, next node identifier, 3 coordinates, primary variables, and then again secondary variables. So that way we can export the pathline, and it's very simple to read that file into any other program and just get some more use of that. Of course, the pathline is a grid as any other grid, so we can apply any transformation to it. We can give it display options, and we can, let's say, hide those curves completely. So I can do anything I do with normal grids. For example, if I just decide to mirror the parent grid, and I can here say mirror also to all these path lines. You see that by using the folder, I just apply the mirror to all of them at the same time. Now, of course, if I just move in one path line, it will be showing me two arrows because it is also mirrored. Now you see we see here an ugly inner boundaries which we don't like. There is a small trick in the boundary conditions. You can right click and say just toggle visibility, and also on the second axis I can just say toggle visibility, and now my axis will be my surfaces with the axis will be not visualized, so I can just do it and see through.